me start the recording. All right, so the last class we're going to study probability now. Well, first of all, we should know how to do counting. Okay, so if you know how to do counting, then we are able to do the math, solve some probability problems. So question, what is probability? Okay, so if you have a coin, right, and the coin has two sides. One side is heads, other side is tail, right? So you have a coin, all right? You have a coin. Oh, that's a coin, right? And this is a head, and here's tail. Okay. Now, if you flip the coin over again, okay. So what do you expect? So you think about half of the time when you flip the head, you will flip the heads, right? And about half time, right, you will flip the tails. So how do we express it in mathematically, right? So we are going to use some number, which is called probability, okay? And then we will say that the probability, okay, that a coin, flip will turn up heads is 1/2. Okay. So I'll give you a little bit more precise definition. Okay, the probability if all outcomes are equally likely, then the probability of a success is the ratio. Okay, the numerator is the number of successful outcomes. The denominator is the number of all possible outcomes. So so-called successful outcomes is just this is the outcomes you want to get. Okay, you want to get. Okay, and let me explain to you using an example. Okay, so here's the first example, very simple. Okay, suppose we roll a pair of six-sided dice, and what is the probability that a 5 is rolled? Let me draw the picture, right? So this is a typical dice. Okay, you have the 1, 2, 3, all the 6 numbers on all the faces, right? So what is the probability of 5 is rolled? So that means, okay, by definition probability, right? The number of possible outcomes, it could be from 1 to 6. So that's a 6. Okay, right? Then the number of successful outcomes, that's what you want to get, right? You only get 1, okay, which is 5. So 5, this is just only 1, yeah. So only one number is 5 among the 6 numbers. So that's why the probability is 1/6. Yes, that's simple, right? Good. And so let's take a look at the next problem, okay? An even number, so an even number is rolled. Now, still, right? Still there are, for the denominator, the number of possible outcomes still 6, because from 1 to 6, right? You have 6 numbers, but even numbers among the 6 numbers, right, are 2, right, 4, and 6. Okay. So you will see that the number of successful outcomes and number of we also call designed outcomes will be 3, right? So clearly, and after you simplify, that will be 1/2. Okay, got it? Just because you have 3 even numbers there. Okay, you have 3 even numbers. Okay. Then the third question is a perfect square is rolled. Okay. So among those 6 numbers, right? How many numbers are perfect squares? Okay. So you have to figure out where is the perfect squares. right? Perfect squares. Right? Perfect squares, it's 1 is a perfect square because 1 square equals 1, right? 2 square equals 4. So 4 is a perfect square. There are only 2 perfect square there. So the probability that denominator is still the number of the all possible outcomes, right? And this is 6 because you have 6 faces of this cube. And then it's on the top, it's 2, so it's 1/3, right? 1/3 is a probability, okay, that a perfect square is rolled. Okay, so we get a pretty good idea about this, right? The probability. All right, and so that means if you record, okay, now if you, if a die is rolled over again, every time you record the information, whether you're going to get a perfect square or you get you're not get a perfect square. Okay, if you record that, and then total number of the perfect square you're going to get over the total number of the total number of the times you roll the die is rolled, right? And you can do that 1,000 times, millions times, okay? And then the ratio will be very close to almost equal to 1/3. Okay, yeah, it's guaranteed. Okay, yeah, that means if a die is rolled a billion times, and denominator will be 1 billion, and then you count those, you got a perfect square. Then you find out more times the die is rolled, and the more close to 1/3. Okay, that's another way to understand the probability. All right, probability is just the numbers of perfect number here, right? Okay. All right, so take a look at the second problem. Okay, this time it's not the 6-sided die. Okay, this is going to be 8-sided. It's hard to draw the 8-sided die. Okay, you can make it 8-sided and the 4 on the top, 4 on the bottom. Yeah, it's hard to draw it. Okay, so but you painted, okay, you painted the 2 red sides, 5 yellow sides, and 1 blue sides, total 8 sides. So what is the probability of a rolling yellow side? Rolling the yellow side. All right. So first of all, right? Okay, I'm sorry. First of all, the denominator, the number of all possible outcomes will be 8. Okay, but you only have 5 yellow sides, so clearly you have 5 possible. The number of successful outcomes will be 5. Okay, you will, because you expect to get yellow sides. Okay. Okay, it's pretty good. So now let's talk about a standard deck of 52 cards. Okay, so let me describe the standard deck. A standard deck cards has a 52 cards divided into 4 suits, each of which has 13 cards. From 1 to 10. Then you have what? Then you have those, jack and the right queen, queens, right? So total 16. 16 times 4, you got total 52. Okay, their names, one called hearts and the dimes, right? And spades and the clubs. Okay, and also white, black, right? Right. So those cards in the deck are placed in a random order. Okay, so we are going to discuss many problems like what is the probability of the top of 2 cards are both red. So we don't care about that right now. Let's look at some problems we're going to study here. Okay, so we consider a standard deck of 52 cards. The deck is randomly arranged. So what is the probability that the top card is spades? Okay. So the top card is spades. How many spades there? 13. Yeah, 13. So the denominator, you have a 52 possible outcomes because there's 52 cards. Spellers, right? That's 13 there total. So you divide, yeah, numerator will be 13. But when you look at 13, yeah, this is a definite, it's right? 13, 52 is divisible by 13 because that's how do we get 52, like 13 times 4. So that's why it's get 1/4. Okay, let's get 1/4. But first of all, you write 13 over 52. Okay. Then you simplify it to 1/4. Then you simplify it to 1/4. All right. And I'm going to ask you to do the next problem. The top one is a 9. The top one is 9. All right. So if you get answers, let me know. Yeah. All right. So the denominator is still 52, right? The denominator is still 52. The numerator, the question is how many 9s there? Everybody knows that. That's 4 9s there, right? There are 4 9s there. Yeah. So you put a 4 there. Then clearly, 52 is, how do we get 52? 13 times 4. So that's why when 4 cancel out, it's get 1 over 13. Okay. So 1 over 13. Okay. All right. So now we're going to look at the next problem. Okay. So the top card is a face card, which face card means a jack, queen, or king. Okay. Now that would be slightly different, right? So you have to need to count how many face cards there in order to solve this problem. How many face cards there? Okay, so denominator, yeah. So denominator is still 52, right? Yeah, the denominator is 52. The number of all possible outcomes still 52. The number of the face cards, so jack, queen, king, that's 3, but you have 2 different colors, right? So 3 times 4, right? So I'm not going to multiply this out. Instead, I'm going to factor this out. 13 times 4 always, 52 is 13. So 4 canceled out. So 13 over, 3 over 13. Okay. You see, if you do the multiplication first, like 3 times 4, you get 12, then all the even numbers, then you try. That's additional. You have to do additional, computations. So it's not necessary. Okay, so something just, that's what I did. Divide by 2, numerator, denominator, and 6 over 26. Okay, let's even numbers again. Then you divide it by 2 again. See how many division you have to do, right? So it's better to keep in mind 52 comes from 4 times 13. Okay, 4 times 13. All right. Yeah. So this is a probability, right? So that means if you randomly pick up a card, right, and you record whether it's a face card or not, and if you tried millions times, okay, for example 1 million times, so chances the total number of face cards you're going to get, which you put in the numerator, and divide by 1 million, and you should get a number not exactly 3 over 13. It'll be very, 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 very close to 3 over 13. Okay, 3 over 13 is the ideal case. Okay, that's what, how do we, yeah, this is an ideal case. It's called a probability. Okay, unlikely you're going to get 3 over 13 exactly, but very, very close. Okay, depends on, you know, how many times you're going to. If you only take 2 cards, possibly none of them will be first card. You can try at home, right? So that does not mean you change the probability. You know, the probability is still 3 over 13. Okay, you have to take many times. Okay, take a card many times, more times. You can do the experiment record. Okay, if you since you have to use a calculator. Okay, so you have a deck of 52 cards. You just write down. Okay, you try 100 times. Okay, randomly pick up a card. If it's a face card, you write down the face. Okay, you count to 1, and then you put it back and then random pick another card. If it's a face card, and record it 100 times. Okay, and you record the total number of the face cards you're going to get, and you divide by 100. Okay, this is not going to be exactly equal to 3 over 13, but you compare those two numbers, the error, the difference is very, very small. Okay, so you gradually understand the concept of probability. Okay, the probability we get here is the ideal number. Okay, and if you're able to do the 1,000 times, I don't think so. 100 times is already too much. Maybe 20 times, yeah. Then you get a number pretty. You get a larger. You get a fraction, okay? Because 20 is in the denominator, and the numerator some numbers, right? You're gonna get. Okay, maybe 4, maybe 5. So you get a number very close to 3 over 30. Okay. All right. So now let's do the next one. The top card is a black, and the second. The top card is a black. Let's see. So this time you're going to. So you're going to take 2 cards. Okay. Yeah, you're going to get 2 cards. Yeah. Yeah. What is the probability that if you take 2 cards randomly? Okay. All right, so you're going to get the top card is black, and the second card is red. Okay, so you just rearrange them, right? So basically, you just withdraw 2 cards from the deck of 52 without replacement. It's the same. Or you just put a deck of cards. You just look at the first one, look at the second one. If the second one is black, the first one is black, and what is that? Second will be red. Okay, what is the probability? Okay, now this is a bit challenging, right? All right, so you're going to have 52 cards here, 52 cards. Okay, so you're going to take 2 cards here. So the denominator, okay, so the number of possible outcomes, okay, is going to be, you put them in the order. You randomly, pick up 2 cards one by one, put them in order, okay? So the first one, you have 52 choices. Second one, you have 51 choices, right? Do you agree, right? That's called the multiplication rule, right? Counting. So you have this many possible outcomes. Now, in order to get the first one is black, second one is red, right? How many red cards there are? 26 red cards. 26 red cards. 26 black cards. Okay. So the number of successful outcomes or the number of design outcomes. Okay, so you're going to get a black car, but only from this group of 26, this set of 26 black cars. So it's 26 choices. Okay. Then, why is 51? Yeah, I'll explain to you later. Then for the second one, right, you can only get from this set of red cars. So also 26 choices. Okay, now why 51? Okay, because you're going to take 2 cars out of 52. So first of all, you pick up 1 car. This should be the car on the top. And there are 52 cars there, of course, 52. Now, how many cars left? 51, right? So second step to get the next, take the next car. Because you do not put the car back, right? So there are 51 cars left. So that's why second step, there are 51 choices. So the total number of the ways to take 2 cars and put them in the order will be 52 times 51. That's called the multiplication rule. Okay, so the probability will be 52 times 51, 26 times 26. Oh, no, sorry, I'm upside down. Yeah. Let me draw it, erase it. Okay, so the numerator is 26 times 26. And then 52 times 51. So 26 is a 2 times 13 times 13. Okay, and the 52 is a 4 times 13, then 51. So 2, 2, 4 cancel out, 13, 13 cancel out. So it's only 13 over 51. So 13 over 51 is correct answer. Okay, so this is a little bit difficult problem, right? Yeah, but we apply the counting principle here. Okay, and remember, when we select the 2 cars, put them in the order. Okay, you just need to figure out how many choices for the first car, how many choices for the second, and then do the multiplication. Okay, okay, then that is the total number of the combinations. Okay, all right, so now now you can do the next one. Okay, I hope you can do that. Okay, so top car is a 3 and the second car is an 8. Okay, so please turn off your video. Thank you. Okay, now if you get it, and let me know. Yeah, the numerator will be a pretty strange number. All right, cool. Someone already submitted answers. And anyone else? All right. So first of all, yeah, it's the same problem, right? Top car, the first car, second car, right? So so how many, how many choices for the first car? Must be 3, right? So it's 3. The number is 3. So 4 3s there. That's 4 choices. And the second car is an 8. So also the 4 cars with the number 8. So that's why you have 4 and 4. So the probability is 4 times 4 here, but the denominator is still 52 times 51 for the same reason I already explained to you. So that is going to be, 4 times 13 times 51, 4 times 4, right? So 4, 4 cancelled out, and 13 times 51, you have to do the multiplication. Okay, 13 times 51 is 663. It's a pretty strange number. Okay, so that's why how do you simplify it? Okay. Yeah. Good. Now, the top two cards are both S's. Both S. Right? And that's slightly different. Okay, it's slightly different. So, right? So we want to get an S, right? And so there are only 4 S's there, right? Only 4 S's. So the numerator, okay, the denominator is a 52 times 51 because you're going to take 2 cards without replacement, one by one, right? Then first, yeah, you have 4 choices, but not 1 is gone. So only 3 left, right? So that's 3 second time, you only have 3 choices. So that's a total number, okay? And you, after you simplify, you have to simplify carefully, okay? So you have to simplify it. It's a 4 times 3, right? 4 times 13 and 51, right? 51 actually is divisible by 3. I can tell that. Why divisible by 3? Because the sum of the integers, right? 51, right? Divided by 3. So it's 17 times 3. So 4 cancel out, 3 cancel out, and 13 times 17. Right? It's 221. Okay. Right? So 13 times 17. Yeah, 221. Okay. Yes. So you see, as you see that I'm not trying to factor them. I'm trying to multiply them out. Actually, I'm always trying to factor those numbers. Okay. At the very beginning, I thought the 51 is not divisible by 3. Then I look at, oh, I remember, how do you check the number is divisible by 3, right? So the sum of the digits is 6, divisible by 3. So therefore, you can always factor 51. Then you cancel all the common terms in the numerator, denominator. Then you do the multiplication last minute. Okay. It's great. All right, so we did a lot of problems here. Now we focus on another type of problems. So suppose we flip 4 coins simultaneously, a penny, a nickel, a dime, and a quarter. What is the probability that they all come up heads? Well, you can put them in the order, okay? Nickel, dime, okay? So this is a, right? So this is a penny, right? And this is a nickel, penny, nickel, dime, and quarter. Okay. All right, so now, so the question I have to figure out how many possible outcomes. Okay, the number of all possible, yeah, the number of possible outcomes, okay? And you look at those 4, right? It's in the order, penny, nickel, dime, and a quarter. There are the two possible ways to write down, if it's heads, I just write H, or, right, H or T, right? H or T, H or T, H or T. So each time I have 2 options. So 2 times 2 times 2 times 2, total 2 to the 4th power, which is 16. So I'm going to get 16 possible outcomes. Okay. So a typical, the typical where you get, sequence you get is H, T, H, H, for example, right? So the penny is head, comes up heads, nickel comes up tail, and the dime comes up heads. and the quarters comes up with heads, for example, right? But you see that each position, it shows up H or T. So that's why I totally have 2 times 2 times 2 times, total 16. But the number of successful outcomes, which is called also design outcomes, in this case, it's only 1 because all of them all come up with hits. So just H, 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 H. So that's only 1. So that's why the probability is going to be 1 over 16. Okay. So let's understand this first. 1 over 16. Okay. 1 over 16 is answer. So now you're able to, let's do the second problem. Okay. A penny and a nickel both come up heads. Okay. So the 4 coins can land 2 different ways, heads or tail. Remember that, right? Okay, if you have answers, let me know. Okay, and I should know how to explain that, right? If you give me that, don't just guess. Okay. So that means penny and nickel both comes up, right? So penny, this is a penny, must be heads. Nickels must be heads. But the diamond and quarter, okay, sorry, my file is gone. Let me bring it up. Just a second, okay. Okay, now it's back. So yeah, penny, nickel, dime, quarter. But the first 2 is a fixed, must be heads. Okay, must be heads. And then the dime and the quarters. Okay, you have there are 2 possibilities for the dime and 2 for quarters, right? So dime and the quarters are free, it's not fixed. So the number of successful outcomes based on the dime and the quarter. Okay. Okay, it's just 2 times 2, which is 4. Okay, because there are 4 possibilities for the dime and 2 possibilities for dime and 2 possibilities for the quarter. And the penny and nickel is already fixed. That's what they want to see. There's no freedom. Okay, just they come up with heads. Okay, so the probability in this case is 4 over 2 to the 4th power, and that is a 4 over 16, and that's 1 over 4. Okay. Yeah. Yeah. So this is a H or T. H or T. So it's 2 choices, and multiply them out. Right? And HH here, for the penny and for nickel, they are fixed. Right? All right. Now, the 4th problem is at least 15 cents of worth of coin come up heads. Now, this is a little bit complicated. You have to do the computation. Okay, the denominator still 16. The numerator will be slightly different. Okay, 15 cents, right? So you get, nickel, penny, nickel, dime, and a quarter. Okay, so we don't know which way it is, right? So the question is, how do we get 15, minimum 15 cents? So you have to divide them into several cases. Okay, case 1, case 2, case, right? So I would like to, quarter. If quarter comes up ahead, okay, then yeah, case 1, okay. So we assume that what comes up at, so you already get 25 cents, so it's guaranteed. So in that case, the number of the design outcomes will be, those no choice, that can be any of them, either H or T tail, right? So you always guarantee you get minimum, right? 25 cents. Okay, so in this case, the number of design outcomes is going to be 2 times 2 times 2, because either H or T, H or T, H or T, and here's H. Okay, that's why you have 25 cents you get. So it doesn't matter whether you get H or T, H or T, H or T, right? So you always guarantee the total value you get is going to be greater than or equal to 25 cents. Okay. So that is the first, right? Now the case number 2. The case number 2, yeah, then case number 2, the quarter comes of tails, right? So in that case, okay, so this, you never get 25 cents. So question is, how do you get 15 cents? Okay, then you divided them into 2 sub cases, right? For the dime is 10 cents, right? If a dime is tail, it's not, you cannot get. Right. So think about this problem, right? So you must, in order to get 15 cents, the dime must come up heads. Okay. Otherwise, you get 1 plus 5 is still 6 cents, right? In this case, the dime must come up heads. So that is also fixed. So let me draw the picture. P and N, D and Q. This is a tail. This must be heads. So 10 cents. Now, in order to get the 15 cents, and I think the nickel must show up, right? Otherwise, you never get the 15 cents. So this also must be heads. Okay, right? So it's 5 cents. Yeah. Then penny doesn't matter. Comes up with heads or tails. So this can be 2 choices. So nickel and dime must come up with heads. Okay, so no, there's a freedom, right? 2 possibilities for the penny. So total, the number of designed outcomes is going to be 2. Okay, so the probability is going to be 8 plus 2 over 16. So it's 10 over 16. After simplifying, it's 5 over 8. Right, 5 over 8 is the answer. Right, so that's what we learned in the last class. We divide them into several cases. Okay, you count them and add them together. Okay, otherwise it's difficult to get the number of design outcomes. So in each case, be much easier. You can figure out the total number of cases. So when the quarter comes up tails, then you see that, in order to get 15 cents, the nickel and the dime must come up heads. Then there's a two possibilities for the penny. So that's why you have two. Okay, got it? All right, so take a look at the next problem. Suppose we roll two fair six-sided dice, and what is the probability that the two numbers rolled, the sum is 5? So now we needed to do some computations. Okay, so we get, right, we got two numbers, right? 6 dice. So we got two numbers. Let me put two numbers here. The number of possible outcomes, right, must be 6 times 6. Right? It's going to be 6 times 6, 36. That's clear. Now you want to get the sum equal to 5. Right? So two numbers. Right? So now you count A plus B equals 5. In order to get A plus B equals 5, you begin with 1, right? So A and the B is going to be 1 and 4, right? Then 2 and 3, right? And the 3 and the 2, and the 4 and the 1, right? So here we count the order because we have the first die, the second die here, okay? So they're independent. That's why you have 2 to 6. Otherwise, the denominator also be changed. If you grab, for example, it's a, so that's why, this is how to get 36. Okay, we don't count the order. The first one, the second one. The first one have 6 choices, second one have 6 choices. So that's why total we have 36 combination. Then the first one is 1, second one is 4. Then it's different from the first one is 4, second one is 1. So that's why the number of designed outcomes is going to be 4. Okay, then the probability is going to be 4 over 36, which is 1 over 9 after simplifying. Okay, all right, so let's move on to the next problem. Okay, so this time is about the product. Okay. About the product. The product of the two numbers, sorry, the product of two numbers you get is going to be multiple of 5. So the denominator is still 36. Okay, the denominator is still 36. So this is the two numbers. Okay, A times B should be the two numbers is a multiple. The product is a multiple of 5. Okay, right? You got two numbers. So the number of design outcomes still 36. The question is, how do we count those a multiple of 5? Now, in order to get multiple of 5, right? One of the how to get multiple 5? So one of them must be 5, right? Right? Yeah, because from 1 to 6, only 5 is divided 5. So one of them must be 5. Okay. If you do that, then be careful, right? So it's going to be it can A and the B, right? So it's going to be you can, let's say, assume the first one is 5. So 5, right? The second one, 5, 1, 5, 2, right? 5, 6, right? And then it could be The second one is 5, right? And the 1, 5, 2, 5, okay, and the 6 and the 5. So total right now sounds like 12, but you have to say that's 1, 5, and the 5 are in comma. You cannot double count it. So that's why the number of successful or design outcomes is going to be 12 minus 1. That's going to be 11. So the probability is going to be 11 over 36. Okay, this is just be careful when you count it, right? Yeah, it's double counted. So that's why I put a question mark here and I have to be careful about this. Okay, otherwise it's 12, right? 2 times 6 plus 6. All right, so now let's take a look at the next problem. A pair of 8-sided dice has the sides of each die numbered 1 through 8. Okay, so you have yeah, a little bit difficult to join. Now something looks like that, Yeah, 1, 2, 3, 4, and another one on the back side. Okay, 5, 6, 7. But okay, so each side has the same probability of landing. Of landing face up. What is the probability that the product of the two numbers on the side that land face up is greater than 36? Okay, so here is we're talking about the product. Okay, first of all, you see that you write down the two numbers, right? Just like that, similar to above. So the number of possible outcomes is going to be 8 times 8. Okay, you can multiply this out or you just keep that 8 times 8. Sometimes you use it for. Now it's a little bit difficult because if this is A and the B, right? You want to count the number of A and the B, okay, such that A times B is greater than 36. All right, so you just need to count those possible products, right? So A times B greater than 6. I think, let's look at the A. Okay, if A is less than 5, then it's impossible because 4 times B, note that 4 times B, the largest value of B is 8, is going to be 32. 32 is less than 36. So it cannot, A cannot be 4, right? Or less than 4. So you have to begin with 5. If A equals 5, then you will see that B must be equal to 8. Then you can get 36. So if A is 6, then B can be cannot be 6, 7, and 8. Okay, so then the product is greater than 36. Okay, if A is going to be 7, B, I think is going to be 6, 7, 8. So if A is 8, so just only a few cases. I think B can be as low as 5. Yeah, 5. 5, 6, 7, 8. So total, you can see that total that's 10 past design outcomes, right? 10 designed outcomes. Okay, so now you get an answer, right? So the probability is going to be 10 over 64. Okay, and you simplify, divide by 2, it's a 5 over 32. So 5 over 32 is correct answer. Okay, so you just divide them into several cases, you count them, okay. Okay, the next problem is a little bit tricky problem. Okay, I'm trying to show you how to do this problem. We don't know how many single women there are, how many married men and their wives. Okay, but that comes up with a pair. Okay, so I'm going to denote X, the number of single women. Okay, and the Y, the number of men, married men. Okay, and then also Y is going to be the number of married women, right? Because they're wives, right? Married women. So we don't know any of them. That's fine. So first question is, what if the probability that a randomly selected woman, we only consider women, okay, is a single, is 2/5. So what is a fraction of the people in the room are married men? Okay, when we talk about fraction, okay, so write down what you are given. We are given the probability randomly select women. So you only focus on women, okay? You select women. How many women there? So number of the all possible outcomes is X plus Y. Why? Because the X married women and X single women. But the probability that you get a single woman, okay, is going to be 2/5. Now, if you can express that statement into a mathematical equation, then you can easily solve the problem. So what do you want to find out? You want to find out the fraction of the people in the room are married men. So this is married man is a Y. So total number of the people in the room is going to be X plus Y, right? Clear? So this become an algebraic problem, okay? This become an algebraic problem, okay? If you understand the problem correctly, and you should be able to solve the problem. Okay, so let's do it. So based on what we have, the first equation, I can 5x equals 2x plus y. So it's 2x plus 2y. So the relationship is 3x equals 2y. Okay, that's the relationship. Now, how can I get the ratio? Okay, so then y over x plus 2y, right? I want to cancel something here. So what I'm going to do is I multiply 2 the numerator and the 2x 2 times 2y, right? Then I replace y by 3x. 2x plus 2, 3x. Then the numerator gets 3x. The denominator gets 8x. So 8/3. So we're done. Sorry, 3/8. Yeah, 3/8. You see? You don't need to know the exact value of x. You don't need to know the exact value of y, which is undetermined, cannot be determined. But you can solve the problem. All right. All right. Similarly, yeah, you have to read the question carefully. You only consider women. You select the women only. That's why it's x plus y here. Okay, women only. Okay, so total number of women is x plus y. Only among the women you select a person which is single. Okay. So now if we change the problem a little bit, if a probability that a randomly selected person, not necessarily women, okay, is single, is 1/5. What fraction of people in the room are male? So in that case, you are given, okay, a person is single is still x, okay, total number of people is x plus y equals 1/5. So that is to say we consider all the people in the room and you select one person, okay, then that person is single, means single woman, right? It's 1/5, and we want to find out y over x plus y. Okay. I think, it's the same idea, you know, right? The same idea. You can solve the equations. Okay, so you will get 5x equals x plus 2y from here, right? Yeah, multiply this out. And 4x equals 2y. So 2x equals y. So 2x equals y. Then y over x plus 2y equals, you replace y by 2x. 2 times 2x, right? And then it's 2x, and here 5x, right? So the answer is, yeah, it's going to be 2 over 5. So that is a, yeah, that is another ratio. All right, so we solved that problem. Great. All right, okay, a little bit more challenging, right? So this is using algebra, you know, to solve the problem. So now let's take a look at the following problem. A number is randomly selected from the set, you know, from 1 to 15. What is the probability that the number is divisible by 3 or 5? Okay, just be careful when you count them. For total, the number of possible outcomes will be 15, right? We just needed to know how many numbers are divisible by 3 and 5. But be careful, you know, those are divisible by 5. Divisible by 3, you just list them. Then those two sets, actually, there's a common area here, right? So 3, right, divided by 3, 3, 6, 9, you know, 12, 15, okay? And those divisible by 5, and you have 5, 10, 15. So you will see that 15 is in both set. So the probability is going to be, first of all, you have 5 here and 3 here. Then you have the -1, right? And then total divided by 15. So the answer will be 7. 7 divided by 15. Okay, just be careful. Don't count count 15 twice. Okay, 2 minutes left. So consider this one. All right, a bag contains 4 red marbles, 6 green marbles. David draws out 2 marbles at the same time. Now, what is the probability that both are red? Okay, so I'll give you 1 minute to think about, and then you post answers, and then I'll show you how to do it. I got 2 different answers. One of them is correct, and the one is wrong. The 4 red marbles and the 6 green marbles. Right, that's in the back. I'm going to take 2 of them out. Okay. All right, think about that. We draw out 2 marbles at the same time. That means, in other words, you're going to draw a marble without replacement. You cannot put it back. You just grab 2 marbles. But you can put them in the order or without, it doesn't matter, okay? The result is the same result. So you grab 2 marbles, you can say 1 by 1, you can put in the order on the table. Okay, suppose you can put them on the table. What do you get, right? So then the number, yeah, put them in order, right? So the probability here is that if the order is not counted, okay, then if the order is counted, the first marble, second marble, then your total, you have 10 marbles there. So the first marble, you know, the number of all possible outcomes, right? Then you have 10 choices. Then you have 9 choices because one marble is gone the second time when you grab them, right? But for the numerator, you only consider red marbles. So the first marble, 4 choices. The second marble, only 3 choices. Okay, so that is one way to do. Okay, so in this case, the order is counted. Okay, so the answer will be, you know, you simplify it, right? It's 2 times 3 and 2 times 5 and 3 times 3. So 3 cancel out, right? 2 cancel out. So 2 over 15. That's what I got, right? 2 over 15. Okay, 2 over 15, 2 marbles. Now this is the way we count the order. Suppose I don't count, you grab 2 and put it in the hands. If you do not count their order, then the numerator have to divide by 2 factorial. The denominator also divide by 4 factorial, but after you simplify, you still get the same result. Okay, in this case, if the order is not counted, but the result will be the same. And here, if the order is counted, but it's without replacement anyway, you can take, right? It's counted. If it's counted, then red marble, green marble, and then switch sort the green marble, red marble, it's different, you know. But if you take 2 marbles out of the bag and put it in your hands, you don't see the order, right? Can be any order, but still the result should be the same. You know, both are red or both are, you know. Okay, if the order is not counted, then we call that pair of marbles. Then you have to divide by 2 factorial. So you end up with as the same. After you simplify, you still get 2 over 15. Okay, 2 over 15. Okay, so those are the basic probabilities. And in the advanced math class, we're going to study more complicated probability problems. Okay.